Good morning, everyone. I am Lakshmi Priya, along with my team members Mamantika and Pujita. We are presenting our final year project titled Two-Stage Cervical Cancer Detection Framework using XGBoost based risk prediction and FastVIT's cytological image classification. This project comes under the domain of machine learning and focuses on improving cervical cancer screening through an AI-powered, explainable and clinically supportive framework. Our project combines clinical risk prediction and medical image classification into a single intelligent system that supports early detection and better healthcare decision making. Cervical cancer is one of the most common cancers affecting women globally. Early diagnosis is extremely important because it can significantly improve treatment outcomes and reduce mortality rates. Traditional screening methods like pap smear analysis are effective, but they require skilled specialists and laboratory infrastructure, which are not always available in rural or resource limited areas. Many existing AI systems focus only on one area, either predicting cancer risk from patient data or classifying cervical cell images. Because of this, they do not provide a complete diagnostic workflow. To solve this problem, we developed a two-stage framework. In the first stage, we use XGBoost along with SHAP explainability to predict cervical cancer risk using clinical and behavioral data. In the second stage, high-risk patients undergo cervical cell image classification using FastVIT and GradCam visualization. We also integrated the system into a Flask-based web application with secure login, automated PDF report, and LLM-assisted summaries to make the system more user-friendly and clinically useful. Existing cervical cancer detection systems usually addresses only on one part of diagnosis. Some systems focus only on patient clinical data, while other focuses only on image classification. This limits their effectiveness in real-world medical scenarios. To overcome this limitation, our project introduces a unified two-stage AI framework. The first stage analyzes patient clinical data using the XGBoost algorithm to predict cancer risk. SHAP explainability is used to show how each feature contributes to the prediction. If the patient is identified as high risk, the system proceeds to the second stage, where cervical cell images are classified using the FastVIT deep learning model. GradCam is used to highlight the important regions in the image that influence the prediction. The entire system is deployed through a Flask web application with secure authentication, conditional image upload, and automated PDF report generation. Our proposed model achieved an overall accuracy of 97.62%, making it an accurate and interpretable solution for cervical cancer screening. To understand the current advancements and limitations in cervical cancer diagnosis, we analyzed several recent research papers related to explainable AI, risk prediction, and medical image classification. The first paper discusses an explainable AI-based segmentation framework for cervical cancer screening. However, the limitation is that it focuses only on image segmentation and does not include clinical risk prediction or a multi-stage diagnostic framework. The second paper proposes an interpretable stacking ensemble model for cervical cancer risk prediction using clinical data. The system combines multiple machine learning algorithms and integrates expert medical knowledge for better reliability. However, it lacks image-based analysis and does not provide a complete diagnostic workflow. This third paper, the research introduces a stacking ensemble model with explainable AI for cervical cancer diagnosis. Feature importance analysis improves interpretability, but the same system does not include cervical image classification or multi-stage diagnosis. The fourth paper, the study focuses on explainable deep learning for breast cancer detection using medical imaging. Although interpretability is improved, the research is limited to breast cancer and does not combine clinical and imaging data. This paper provides a review of AI techniques used in cervical cancer cytological diagnostics. It discusses image processing, deep learning, and explainable AI methods, but it does not propose a practical integrated framework. This research proposes a transformer-based model for cervical cancer risk prediction using clinical data. While the model achieves good prediction accuracy, it lacks explainability and image-based validation. This paper introduces a CNN-based cervical cell classification model with casual interpretability. Although it improves image classification reliability, it does not include clinical risk assessment or multi-stage decision making. This study uses machine learning models for cervical cancer prediction based on blood analysis. The approach supports non-invasive screening, but it lacks explainability and cytological image analysis. So what I would like to conclude is, from the literature survey, we observed that most existing system focuses only on either clinical prediction or image analysis. Very few systems provide an integrated, explainable and practical framework. This research gap motivated us to develop our two-stage cervical cancer detection system. What are the issues and challenges faced? During the development of our system, several challenges were identified. The first challenge was class imbalance and noisy medical data, which can reduce prediction accuracy. The second challenge was the black box nature of deep learning models, making predictions difficult for doctors to trust. Another issue was the limited availability of specialists in rural healthcare environments. We also noticed that many existing systems lacked secure authentication and automated reporting. Finally, scalability and accessibility were limited because many solutions were not web-based. Our proposed system addresses these challenges using explainable AI, secure deployment, and an integrated web-based framework. This diagram, the module architecture diagram, illustrates the overall workflow of a proposed system. The process starts with user authentication and clinical data collection. The data is pre-processed and passed to the XGBoost model for risk prediction. If the patient is classified as high risk, cervical cell images are uploaded and analyzed using the FastVIT model. SHAP and GradCam provide explainability for both stages. Finally, the system generates an automated PDF report along with an AI-assisted summary. The proposed architecture. In the first stage of our architecture, patient demographic, behavioral and clinical information is collected through the web application. The data then undergoes pre-processing where missing values are handled, categorical data is encoded and numerical values are normalized. The process data is passed into the XGBoost model which predicts cervical cancer risk. To improve transparency, SHAP explainability is applied to show how each feature contributes to the prediction. Based on the prediction probability, patients are categorized into low risk or high risk groups. For low risk patients, the system directly generates an automated PDF report. For high-risk patients, cervical cell images are uploaded for further analysis. These images are classified using the FastVIT deep learning model into a diagnostic categories. GradCam visualization highlights the regions in the image that influence the model's decision. The system also calculates confidence scores to indicate prediction certainty. Finally, a detailed PDF report is generated containing diagnosis results, visual explanations, and confidence scores. An LLM-assisted summary is also provided to help clinicians understand the results more easily. The hardware requirements for a system include a minimum of 8 GB RAM for smooth execution of machine learning and deep learning models. An Intel i5 or higher processor is recommended for efficient computation. A GPU is optional but can significantly improve deep learning inference speed. At least 50 GB storage is required for datasets, trained models and reports. A stable internet connection is needed for deployment and remote access. Software requirements. Our system was developed using Python 3.10 as the core programming environment. Flask was used for developing the web application interface. XGBoost and scikit-learn libraries were used for machine learning based risk prediction. PyTorch and FastVIT were used for deep learning image classification. For explainability, SHAP and GradCam techniques were implemented. User and data management module. This module handles user authentication and secure data management. It supports user registration, encrypted password verification, and session-based access control. Clinical data entered by users is validated to ensure consistency and accuracy. SQLite database is used for secure and efficient storage of patient records. Role-based access control is implemented to manage permissions for different users. Risk prediction and explainability module. This module focuses on clinical risk prediction. Patient clinical parameters are converted into structured feature vectors. The XGBoost model predicts cervical cancer probability based on trained patterns. Patients are categorized into different risk levels according to prediction scores. For low-risk patients, PDF reports are generated automatically. SHAP analysis explains how each feature contributed to the prediction, improving transparency and clinical trust. Image analysis and reporting module. This module handles cervical cell image analysis for high-risk patients. Image upload is enabled only when necessary, reducing unnecessary processing. FastVIT model performs image classification and predicts the cervical cell category. GradCam highlights suspicious image regions influencing the prediction. The system automatically generates structured PDF reports containing classification results, prediction scores, and medical recommendations. Output screens. These slides shows the implementation outputs of our system. Here we can see the user interface, patient data input processes, prediction outputs, sharp explainability results, image classification results, GradCam visualizations, and automated PDF report generation. These are the various references that we have used, the research papers and journals we refer to during the development of our project. They helped us understand the latest advancements in explainable AI, machine learning, and cervical cancer diagnosis systems. Finally, to conclude, our project presents a two-stage explainable AI framework for cervical cancer detection. The system combines clinical risk prediction and cervical cell image classification into a unified workflow. By integrating XGBoost, FastVIT, SHAP, and GradCam, we achieved both high accuracy and interpretability. The Flask-based deployment, automated reporting, and AI-assisted summaries make the system practical and user-friendly. In the future, this framework can be extended using larger datasets, cloud deployment, and real-time hospital integration. Here comes the implementation flow. Thank you.